So, hi, this is Arun. Today is a festival in India. We are from the India actually. So the festival name is Diwali. So I wish you happy Diwali to everyone. And this is my introduction. It's like my name is Arun Mane, and I'm founder and director of Aminasec Labs. It's recently we launched company, and my interest lies in hardware security, IoT, vehicle, and ICs as well. So I'm a speaker and trainer of a lot of conferences like Black Hat, DEF CON, and NullCon, HITB, what's not. And this is my Twitter. If you really want to reach me, you can reach me on this Twitter, and this is my email ID.
Hello, I'm Nikhil Bogam. I'm basically safety and security manager at Lear Corporation. I have almost decade experience in automotive. Recently started with cybersecurity in the field. I'm a speaker also in RootCon, Cocoon, OAP sides, B sides. So yeah, that's it. Thanks.
So what exactly the car? So this definition to those people who don't know what exactly the cars. So it's a four-wheeler. More than you can see the more than two wheels you can see, and it transports the people from one location to another locations. So yeah, you can see on the Wikipedia as well. So what exactly the comms in the car? So if you see a lot of communications over here, like transmission control unit and key fobs and anti-theft, OBD2, TPMS, there are different kind of communication you can see on the vehicles. So now you can see it comes connected with the Wi-Fi, Bluetooth, and the cellular technology as well. So there are some devices which comes with the third-party vendors. Now, if your car is not smart enough, so you can put those devices in the car, so it can be a smart car as well. So we are going to jump on directly to OBD2. So OBD2 is onboard diagnostic connectors. So if you see here the 6 and 14 pins. 14 is for the CAN low and the CAN high. So nothing but we are talking about the Canbus protocol. And for the ground, they have ground chassis and ground signals. So this is OBD2 port. If you see in the European, they call it as the EOBD2, EOBD, that is European onboard diagnostic, and you can find those connectors in a lot of cars. Like here is near to driver's seat, below the driver's seat also. And you can see over here as well, these are the OBD2 connectors. So you can use some sort of OBD2 to DB9 or the OBD2 to USB connectors, and you can connect. And if you have those devices, hardware devices, which can talk on Canbus, LIN protocol, and other UDS packets and everything, so you can directly communicate with the cars, and you can sniff communication. You can do a lot of, but it's just a physical testing or other physical hacking, you can say. So some sort of some cars you can see those kind of the structure OBD2 connectors. So you need to buy those connectors, and which converts to USB or other DB9 connectors. So this is typically the ECU. ECU is engine control unit. If we talk about the engines, if we talk about the other comms like the airbag and other systems, brakes and everything, we call it as a electronic control unit. So these nothing but the embedded device which comes with different flavor of chipsets. It may be ARMs, or it may be NXP chipsets, and the entire code is on these embedded systems, and this takes the decisions. It runs the entire vehicle as well, and or rather you can say vehicle communications. So this is, if you see, these are the internal things. If you go from higher end, you can say the cars. So you will see the lot of ECUs inside the cars. And if you talk about the smart car, rather any smart car, you will see more than 200 ECUs inside the car. So you can see. So if you compare the entire the line number of the line code lines with if you compare to Facebook, it's so bigger, right? So it's in billions lines of codes inside the ECU itself. So it's a huge complex technology you can see in the car. So this is what the some sort of features and the associated features comes with the comms as well, the battery management, fuel and internal composition, injection, hybrid motor controls. These are a ton of things you can see in the cars as of now. So it may be a smart car, electric car, autonomous car, anything. So these are the some kind of the sensors or the features inside the you can say vehicles. So if you see the protocol, so if I do the requirements versus the data rate, so the speed you can see the LIN, CAN, then flex ray. So if you see the LIN protocol, it's a one wire protocol, and the data rate would be a very less, and the requirement also is a race in the market. So if you compare with the Canbus, so you will see the most of the cars works on the Canbus as well. So now the Canbus comes with the Ethernet communication as well. FlexRay is again the data speed which is very high as compared to the LIN and the Canbus protocols. So if I talk about the CAN bus, it's nothing but controller area network. You can see those particular CAN bus. You can see in different vehicles. They have extended protocols as well based on the CAN bus as well. So it's a two-wire communications, CAN high and CAN low. I shown you some OBD2 connectors. They have a 14 number is CAN low, and the 6-pin number is CAN high. So it also supports the OBD2 connectors, and it works on the differential signaling. So you can see these are the signals which represents CAN high and CAN low. And if you see the arbitration ID and the DLC in data and CRC field, these are this packet structure. So the Canbus has Canbus 2.0 has two types, like Canbus 2.0 A and B. So difference is the arbitration ID. So if we talk about the Canbus A, is nothing but 11-bit, and if we talk about the Canbus 2.0B, it's a 29-bit identifier. So this is how the data packet. And so it's a CAN extended protocols, some of the ISO-TP protocols, some kind of transport protocols. CAN open, it's another kind of Canbus open source protocol. You can see in different automation sectors, industrial control systems. So and in the robotics as well, some cameras they use Canbus CAN open protocol. GMLAN is another the protocol which it's kind of the proprietary protocol from General Motor. ACI 1850 protocol, PWM, and keywords protocol, and ISO 9141. These are the different kind of the protocols, which is again extension of the Canbus protocol. So if I compare to OBD2, here we talked about the CAN high and CAN low. That's a 6 and a 14 pin number. And if you compare with all extended protocol, you can see that every pin has a different meanings, or rather you can say different definitions, or other pin IDs you can say. So what kind of attacks you can do on the Canbus? First, we do a DOS attack. So what exactly when happens when you sniff the entire communications with respect to OBD2, or other if you attach those hardware which can receive the CAN message with the ECU as well, you will see a lot of messages. So the identifier, the arbitration ID, it should be less. If it is less, that means the message is associated with that ID is on higher priority. So you can see the breaks and other sensitive functions or events has a arbitration ID is very low. So if the indicator shows 200 or other 241 arbitration ID, so if you see the break has a arbitration ID like a 50. So 50 would be the high priority message in the Canbus. So Canbus is like a broadcasting message. When it sends message, it broadcasts the entire message to the Canbus network. So whenever it comes to the particular message ID or other identifier, it listens and gives the response based on the or other gives the events based on the message. So once you know the arbitration ID, and in DLC, if you see send 000 8 byte the zero information or the data, so it creates a DOS on that particular arbitration ID. So these kind of attacks you can do. Firehose is nothing but once you sniff the entire communication, and if you see the timestamp between the two consecutive messages, it would be always less. It would be particularly the time, and if you send those messages within less time, like if it is 2 seconds and if you are sending 1 second on, so it will be the firehose attack as well. Packet payload modification, you can do a lot of payload modification on the DLC itself. Packet replay attacks. So again, if you dump the entire communication and you can replay it, and you can see the same effect on the particular ECU as well. Right after, right before is those kind of attacks when you send the valid message, and after that you send the malicious message, and you can see the difference on the what's the attack or other response on the particular ECU or other in the car as well. And again, if you send the malicious message, and after that you send the valid message, you can see the difference. But specifically when we do the testing of the gateways or other switches in the cars, so these kind of attacks you can do in testing those things. So next is lean network. So Nikhil will tell you about the lean network.
Okay, thanks Arun. He tried to explain about the CAN, and now I'll try to explain about the lean protocol, how it works. We'll start with the lean network here. Basically, lean is the master-slave type of communication. You will see that there are some arrows going on this bus. Let's ignore the first thing here. There are two arrows, but let's see that the master sends information on the bus, okay? So what it sends ID, and then it goes to all the slaves, like slave 1, slave 2, you see these arrows are going there. And then this ID, whoever slaves match, this slave will respond to it. So it is transmitting from here and going to the all other, basically, we can say, to the nodes, okay? Okay, yeah. So now we understood that how this basically the network works, and we'll go a little bit detail inside it. So master sends the ID on the bus. So you will see the ID is reflecting on the bus here, and the slave one responds the 8 byte of information after that. Okay, and the CS stands for the checksum. It also sends the checksum, and if you see the bus, how it look like is there is an ID and the 8 byte of data plus checksum. Okay, so this is how the lane frame is been made. How this lane scheduler works. So master sends the IDs with a particular frequency. So let's say this is a 55 ID is sent, and the slave one responded with 55, a data length of 8, and with the checksum. For the slave 2, the ID is 04, and you'll see that the data is over here sent by them. On the bus, how it look like? It look like that there is a 55 ID and the data, and 04 and basically the data. But we don't understand from where this data came from. Is it transmitted by the master, or is it transmitted by slave 1 or slave 2? This is not possible to distinguish. somehow, and that's the advantage the attacker can take over here. Okay, so we'll see some slides over here after the slide how the attacker can take the advantage of it. This is one more thing which it's like you're allowed to send, the master is allowed to send any ID on its bus. It's basically decided based on how frequently this information is going to be used, and that's why I just wanted to make one additional thing, like the master can send 1004 ID and then the slave to respond to this ID. Okay, so as I discussed earlier, that what the problem on the bus is that we could not able to understand who is sending which data. So that's the advantage the attacker can take over here. So master sends the ID, okay, it goes to all the slaves. Let's say one of the slave is the attacking slave. Okay, so what it does, immediately after sending a master ID, it sends the information on a first byte of data, and what will happen in this case is the collision. There is an important thing in this type of communication. If slave 1 sends positive or 1 on the bus, and the attacking slave sends 0 on the bus, the 0 wins in this case and continues to transmit the data. We will see here how it happens. So there is a master here which is sending 55 ID, slave 1 trying to send the information 80. So 80 means 1 0 0 0 0 0 if you convert into the binary format, and then the attacking slave, so it's somehow not visible here, but it's the attacking slave is sending 0 information over. He wanted to make the other slave to stop its data. After, if you remember that there is a slide I've shown you, it also receives the information. So whatever he puts on the bus, it also receives it. And in this collision, the slave 1 will understand that the attack is, or not basically an attack, but the slave will understand that there is a problem on the bus, maybe it's a fault, and it will stop sending the information. What the attacker slave now can send the data whatever it wants after that byte. And on the bus, it is like no fault, normal message has been seen by the other slaves. So if the slave 1 is trying to send the information to the slave 3 or 4, it's like first byte, he cannot do anything, the attacker cannot do anything, but the other bytes of information he can manipulate, and the change in the functionality can occur in the other slaves. Okay, so this is about the slave attack, he can do it. There is other possibility, lean master attack also. So the master is basically controlling the whole network, sending the different IDs on the bus, but if the attack ECU, it can be a slave ECU as well, or any node connected to it, just sends just garbage value or 000 or something like this, the master could not able to send the information on the bus, which results into something like this, that it sends 55 on the bus, but nothing. On the bus, it's 0, and everybody recognizes that there is a problem in the bus. So it's again try it after some time and check if this is fine. Still, you'll see that the bus is 0. It attempts for some time. After a few attempts, the master goes to a state which is called as error state and stop sending this information. And the next thing what will come up is this attacking ECU will become a master and try to control the whole network. So these are the two types of possible lean attacks are. How we try to do collect this information? We use one of the device from Microchip. It's quite cheap, around $30 or $40 CAN analyzer. You can get it from there, and it gives you the data information. So I just try to show you how we try to analyze it. It also shows the checksum over here. Okay, and this is we tried one lean attack on a slave. This was the data sent by one of the slave. This is the data, okay, and now the same ID is being sent by the master. Now the attacking ECU has made 00 on the first byte of the data, first byte, and the other bytes, the attacking ECU can send whatever it wants. So we just set to send as a 1, 2, 3, 4, 5, 6, 7, and the calculation of the checksum is also been calculated by the attacking ECU and sent on the bus. So these are the basic threats. So we see that on the lean bus, it can occur. Okay, the next about the tools, Arun will take over on it.
We understood the Canbus and lean. The only the thing is, what kind of devices we used for attacking Lin protocol and the Canbus protocol. So value Can3 is one of the tool which is commercial for interpret, and it's cost around I think so $300 to $400 and the software also Vehicle Spy is costly, so it's more than $2,000 as well. So you can use the USB tin. USB tin, it's cost around 35 euros. You can search for USB tin. You will see the sketch. You can print those PCB boards and you can buy those chipsets. These chipsets is nothing but from the microchip, and you can solder and you can start working on the Canbus as well. So there is another called as Can Triple. The same, they use microchip chipset, and it use Can Socket utility in the Linux as well. There is a very nice tool, Can Badger. It's again open source tool, and these are the both guys, good guys from who made the Can Badgers, Fardi and Javier, and they have the tool. And if you see the bomb, so it's like it use 2 DB9 cables, 1 SD cards, and it's like a burp suit style tool. You can intercept the communication, it can replay it, even you can change the message on the fly, and you can fuzz ECU as well with the help of UDS packets, and you can dump the firmware from the ECU as well. And the assembly cost is around $25. So if you take the entire bomb, so it will cost around $100, and it's very good for a man-in-the-middle attack on the Canbus as well, because it supports 2 DB9 cables. So you need to have the DB9 to OBD2 converter, rather you can say the cables, and you just attach over here, and you can start intercepting the communication, and you can do a ton of things. Can tools, again, the Russian guys, they made tool, very nice tool. It's written in the Python, Qt and Python programming language. And it supports USB tin, triple, and a lot of open source tools you can use. It based on the Can Util, Linux utility, and very nice tool, and you can use for fuzzing as well. For Lin protocol, you can there are different kind of vendors in the market as well. You can check for the vectors. We can check for the interpret tools which supports Lin protocol as well. So for very cheap things, it's like it's cost effective. It comes in $25 to $30, and it's the software is also open source, is free editions. So we call it as a Lin serial analyzer. So you can intercept all the communications of the Lin protocol, and you can do ton of things. So this is the main topic over here. So why we understood the Canbus and the Lin protocols, because we should come up with something called as anomaly detection systems, which can detect all type of the attacks associated with the Lin as well as the Canbus. So this is how the actual flow of expected Can message flow and the actual Can message flow. So nothing but we understood the entire the communication, vehicle communication, understand it, and we start analyzing based on some algorithms. We can see we'll see in the next slides, and it shows the alerts as well. So why we require those kind of technologies, anomaly detection systems. If we compare with the IT, it's intrusion detection system. It's the same as anomaly detection systems based on the packet patterns and some sort of different kind of algorithms which are associated with the Canbus and the Lean. So it's easy to adopt in the existing CAN network. So it may be if you come up with the libraries, you can give it to the tier 1 or tier 2, so they can embed the entire ADS library with the ECU, and they can make ADS as well. So it's really easy to adapt, and if you come up with a hardware, you can put it in the network and it can start detecting those attacks as well. So it's a low cost, and it's like when it comes to the ECU modification, it's easy to use that. So CAN network. So Nikhil will tell you the entire how we can go with the ADS with the Canbus.
Okay, thanks. Okay, now we come in the mitigation part, started from Arun's side. So this is basically a network in the CAN bus, how it connects. So it has different ECUs, and anybody can send the data on the bus, and whoever needs the data can read the information from the packets. Okay, so how we can connect to ADS? ADS is easy to connect, so just connect one of the node on the bus. This is one possibility of the ADS. There are many possibilities. You can integrate into one of the ECU. This is also possible. Or you can integrate in all the ECUs. That is also possible. So ADS is nothing but an algorithm to detect if any intrusion is occurred on your network or not. Okay. So let's see what are the types of ADS methodologies are there we can detect. Before we go forward, we will try to understand how this can actually transmit on the in terms of timing. We have seen that the messages are going on the bus, but how it goes. So ECUs, in the automotive world, we call it as an electronic control unit. So any electronic control unit which has a capability to send the CAN messages, generally they send with packets with some time interval. So they don't generally send like an event bus. If you turn on the lights, at that time one packet is sent. It's not like that. Every time, every 100 milliseconds or 500 milliseconds or 1 second, these packets are sent by an ECU. So if you say me how many really such ECUs are there, those are sending frequently messages, I would say more than 90 ECUs are there. And maybe it will be more than 90 also in the coming years. Okay, so ECU1 is sending the message with an interval of 1 second. ECU2 is sending a message with an interval of 500 milliseconds, and then ECU3 is sending a message with 250 milliseconds. So this is generally the CAN transmission is done. Okay, whenever there is a collision, so if you see that the packet 03 and 05 will have a collision, but it somehow has a resolution without impacting the packet format. So if this is a 03, 05 collides, you will get 03 as a precedence. Generally the zeros are in the CAN and the Lean network buses that gets the access to the bus, and immediately after 03 you will receive the 05 can be retransmitted. Okay, so how we can detect if there is an intrusion occur. So one way is to check how frequently these packets are going on the bus. So as I stated earlier, many ECUs are sending this information frequently. So one possible way is you check how frequently is this message are coming, and if they are, let's say we can keep a window, something like this, and if it goes beyond some window, then say that this packet is somehow not been sent by a legitimate ECU, but some intruded or some another ECU which has been sending this message, attack ECU basically. Okay, so this is one type of method we can apply. There are many. So this is another type of method you can apply. You can filter out the messages. Those are not expected. Generally, to carry out a DOS attack, fuzzing, or something like this, the attacker uses the messages which are with a very high priority. So 0 has the highest priority on the bus. So if somebody transmits a 0 message on the bus, nobody gets access to the bus. So he can keep on transmitting and lead to a DOS attack. So none of the ECU can able to send the packets and receive the appropriate information. One way is that you filter it out. If you check that, so you will say, okay, we understood that this attack is occur. What to do with that? The car is more not like an IT systems are, where you have some warning system or something like this. You're driving at 200 km/h and your bus is not working, is not a good idea. So automotive ECs are somehow embedded with software included that they, whenever something happens which is not usual, like the messages are not coming, it goes into the safe state, and which indirectly turns into a safe mode car. So maybe you have an automatic car and then you want to operate a steering wheel, maybe the messages are not coming, it will convert that into power steering to a normal steering, but it will not impact like steering really moving on the left side or moving on the right side. It doesn't do like that. So this is another type. This is a third type of possibility. So all these methods we try to apply on the ADS is on the protocol level, not on the functional level. So there are ADS comes with the functional levels as well. But these are easy to implement. So what it does, it checks what's the earlier message was there and what is the current one, and based on that it decides. So it has to learn all this information, that what was earlier came and then what is the current one, and then it keeps this sequence stored in the memory in the learning phase, and there is an actual execution going on in the car. At that time, it checks if this sequence are actually repeating or not. So you will be in doubt, okay, the sequence might have a problem. It might work sometime, it might not work sometime. Yes, you're right. It might work and might not work and can give a false positive. That's why this is not generally directly read and kept. You check the probability, how frequently this sequence comes. And based on that, you can reduce the false positive. And this is how well the automotive world is thinking about. Okay, one more important thing. We all talked about a lot of things on the network, buses, but it's not so easy that you analyze all this information. And that's why many people nowadays are using AI method to read and understand how this is working. They drive the car maybe for a month or something like this in a different situation. They get this information from the network, store over there, and then in the execution phase, the stored information somehow is used for an algorithm which can able to detect such a type of intrusion. And to reduce the false positive, like we already know about the autonomous driving, we use the AI technology to understand the different situation, and we need to do something like that for the ADS as well. That's somehow to reduce the false positive on it. Okay, so we have seen the type of ADS we can use for the CAN one, but now for the lean it's different, because there is only one master which controls it, and how to do that. The sequence is also fixed, okay, but what we can do over there. So we had a proposal that we have done two possibilities here we can do. We can check the range of the data, okay. I can understand that this will not definitely solve our problem. Also, we can do encryption there, but we also thinking about checking the transition data. This is still make a little bit difficulty for a person, for an attacker to get this transition data, because OEM generally don't share the functional information on a network, how it works. That's what we think. We are working on lean. Still our work has not been finished, and we are thinking of different methods to be used for the lean as well. Okay, now Harun will show the demo which we have done in our lab. So this is our anomaly detection system and how it works. Harun will, I'll explain. So what exactly, can you pause it? What we try to do is, the LED is blinking over here. So what we did is in the lab, we have two ECUs. So we started electronic control unit. The LED blinking is, it's somehow saying that whatever is coming on the CAN bus is all is problem. So what we did is we press that button and it learns that whatever message is going on the bus is the legitimate messages. Now you see the speed transmission ECU is sending information on the instrument cluster. You can see the speed is increasing. It goes till 180 kilometer per hour. And you can see this, the burst information, the data we are sniffing from it. Now, what we did, if you go back a little bit. Yeah. So now we are trying to spoof a message which can change the speed. Okay. We can start that. Yes. And now you see we use this Windows. You see that the speed is changing. It's not taking the information only from the speed transmission ECU and anomaly detection system over here. So you see that the anomaly ECU is capable enough to detect if any malicious messages are coming. So if you see earlier, Arun has explained the packet has the ID, it has the data and the checksum. The same packet who transmitted on the bus could not be identified, but such a type of anomaly detection system can able to detect the sequences, the filters, and maybe a different kind of algorithm can detect such a type of attacks.